Hello BC Calculus students, this is Mr. Johnson and this is section 4.6, which is on optimization. And keep in mind that optimization is just a fancy way of saying that we're going to minimize or maximize a situation. So as an opener, let's review how we've done this in the past. So number one, we've used the extreme value theorem. The extreme value theorem is also called the min-max existence theorem, and that is to find an absolute max or an absolute minimum on a closed interval of a continuous function. Number two, we've used the first derivative test. That one's very common, and it does find the relative maxes and mins unless it is the only relative extreme value, and then it is the absolute extreme value. And then number three, we've done the second derivative test. And this might have occurred, when you have something about the first derivative, such as that the first derivative is 0, but you have no other information about the first derivative, and so therefore you go maybe to the second derivative to see the sign of the second derivative. All right, what we're going to talk about here is just how we're utilizing some of these tests to find a maximum or a minimum in a situation. So we're going to optimize more of a real world situation. Here are some steps that we can follow if it is a situation where we might want to draw a diagram that might be helpful. But you want to make sure to label everything appropriately. You want to work with typically your first derivative to analyze the sign change, whether it's a maximum or a minimum, and then you can read through the rest of those with regard to often the steps that are taken with optimization problems. Let's go ahead and try example one. So we have a rectangular area that is enclosed by a wall on one side and fencing on the other three sides. So let's say this is our wall here, and then we have our fencing, which might look like this. Okay, 18 meters of fencing is used. What is the maximum area that can be enclosed? So let's go ahead and just label these as Y and then X just to make it easy. And we know that the area of this situation is going to be simply X times Y, just one side of that enclosure by the other side. We also know that 18 meters of fencing is used, and based on our diagram that we can see, we have one X side and we have two Y sides. And so that would be an equation that would relate the amount of fencing that we have available. Now to find the maximum area, we're going to want to maximize the function a, the maximum of the area. So we want to find a prime. We want to find the derivative of a so that we can figure out what that maximum might be. But the easiest way to do this is to make a just one variable. And so we're going to solve this for x, and then we're going to substitute that in to the equation for a, so that now we have a equal to 18 minus 2y, that quantity multiplied by y, or maybe more simply, we have 18y minus 2y squared. So again, we're trying to maximize a by taking the derivative and finding the sign change that occurs for maximum. We're hoping that we have just one relative max, and therefore it's the absolute max. So we have the derivative, which is 18 minus 4y, and we're going to set this equal to 0 and solve for y. So y is 18 over 4, which is the same as 9 over 2. Let's take a look at the sign change that's occurring. So with a prime, we have one critical point, and if we were to test a value less than that, we would have a positive number. If we tested a value greater than that, we would have a negative number. And yes, there are some additional parameters to this. Like for instance, you can't have negative side lengths for the practical situation we have here. Also, there is a maximum. We can't keep on just adding more and more fence. But we don't really care. All we know is that we've just exhausted every real number on the number line, and there's one critical point, and there's a sign change from positive to negative. Since that's a relative maximum, and it is the only relative value on that interval, on the entire interval, then that is our absolute maximum. So in this problem, we're not looking at a free response justification. We're just trying to figure out the maximum area. We found, remember, the y value here. And so we're going to go back up to the problem, and we're going to take our area, which is equal to, I'm going to actually select this one. So we have 18 minus 2y. So that's going to be 18 minus 2 times 9 halves, which is just 9, multiplied by y, which is 9 halves. So we have 9 times 9, 81, divided by 2, which is option E. Okay, let's go ahead and try the next problem. All right, in this problem we have the speed of a runner, and we're looking at the function f of m, which is the speed modeled by the runner, and in this particular problem we're looking for the maximum speed on the interval 0 to 3, which again, this is kind of a prime extreme value theorem problem, but it is multiple choice, so we're going to utilize just some intuitive thinking here as we work through the problem. So the first step is we're going to take the derivative because we're looking for a sign change from positive to negative. Remember, the coefficient 1/10 we can just leave out. That's just coefficient, so we could just take the derivative and multiply by 1/10. So we have negative 6m squared plus 18m minus 12. We're going to set this equal to 0 and solve. We're going to want to factor out a negative 6 here. So we have m squared minus 3m plus 2. So in factored form, we have negative 6 over 10 times m minus 2 times m minus 1. So our critical points here are 1 and 2. Let's go ahead and test the sign change for f prime. And again, we have 1 and 2 as critical points. And similarly, if we were to test values, I've talked about this in other videos, if we think about the original function, it's a parabola with a negative leading coefficient, so the parabola is going to open downward, and we just found the x-intercepts. And if that's the case, we know this is negative, positive, and negative. Now remember, we are stuck on the interval from 0, so let's go ahead and just kind of think about, okay, here's 0, and then we're stuck here at 3. Now we're looking for the maximum, okay? And we know that there is a relative maximum at 2. The problem is it is not the only relative extreme value. And so we can't do what we did in example 1, because what if, hypothetically at 0, the function started off really high, and then it decreased, then it increased again, but not as much, and then it decreased. So hypothetically, there could be a maximum here at 0, or there could be an absolute maximum at 2. We know there's not going to be an absolute maximum at 3 because we've decreased from wherever we were at 2, so that doesn't make any sense. And we also know that this is a relative minimum, and there's obviously no way for a relative minimum to turn into an absolute maximum. In other words, we're testing f of 0 and we're testing f of 2. Those are the only two possibilities out of all of our critical points and our endpoints for which we could actually have an absolute maximum. So at 0, it's pretty easy. We get 7. That's a pretty simple calculation. At 2, we have 1/10, and that's going to give us 2 cubed, which is 8 times negative 2, so negative 16, plus 9 times 2 squared, that's going to be 36, minus 12 times 2, so minus 24, and then we're adding 7. So let's see, this is negative 16 minus 24 is negative 40 plus 36 is negative 4. And that's really all we need to know. That's going to be less than 7. So our maximum actually occurs at f of 0, which is a maximum speed of 7. All right, let's try our last example. So this is actually a related rate, connecting back to a couple sections ago. And we have a cup that is in the shape of a right circular cone, something like this. And in this particular case, the height is 12, and the radius of the opening is 3. Water is poured into the cup at a constant rate of 2 centimeters cubed per second. So we have dV dt equal to 2. What is the rate at which the water level is rising? Okay, that's going to be dH dt. That's our unknown. When the depth of the water is 5 centimeters, so when h is 5. Okay, we are given the volume, which is 1/3 pi r squared h. The problem is we don't want the R, we want just the H, because remember, based on our information, we have information about H, and we're trying to find dHdt. So we're going to start over here with the idea that the opening is 3 centimeters, that diameter, or the radius, excuse me, and the height is 12. So we know that the height is equal to 4 times R, or another way of writing this would be that R is equal to H over 4. And we're going to use that in our equation for volume over here. We're going to make it 1/3 pi times H divided by 4 squared times H. And let's go ahead and simplify that. So that's going to give us, this is going to be 4 squared, which is 16 times 3 is 48. So we have 1 over 48 pi times H cubed. And that's going to be our volume that we're going to differentiate. And we're going to differentiate with respect to t because all this is changing by time. So we have dv dt, which is equal to 1 over 16 pi times h squared times dh dt. So again, a related rate. We did that in section 4.1. Okay, we're going to go ahead and substitute in all of our values. So remember, dv dt is 2, and h is 5, and dHdt we're trying to figure out. And so if we were to just move our values over by multiplication or division, we end up getting 32 divided by 25 pi, and that's going to be the rate of change of the height. And that option is letter A. All right, that does it for optimization and section 4.6. Thank you.